Hello everyone! In the previous course, we discussed some of the working mechanisms of WLAN, including its messages, negotiation processes, and more. Now, during the operation of WLAN, what specific protocols or messages are used, and what is the connection between AP and AC? We will introduce these in the upcoming classes. We know that FAT-AP incorporates WLAN's physical layer, user data encryption, user authentication, QoS, network management, roaming technologies, and other application layer functionalities into one. But with the development of wireless networks, the need to deploy wireless devices is increasing, and the drawbacks of FAT-APs are becoming apparent. Currently, almost all enterprise WLAN networks are using the networking method of thin AP plus AC. Between thin AP and AC, STA and thin AP, and the working mechanism of STA moving between different thin APs, there are significant differences compared to FAT-AP. This part mainly introduces the technical background and working mechanism of CAPWAP tunnels, key messages of the WLAN network, and the roaming mechanisms and other working principles of WLAN. Next, we will learn about CAPWAP tunnels. The CAPWAP tunnel is actually what was mentioned earlier. FAT-AP can no longer meet our network requirements, cannot achieve unified management, cannot facilitate troubleshooting, including mass deployment is not appropriate. FAT-AP can only be deployed in small quantities. For example, a typical campus network contains about 1,500 APs. Unpacking these 1,500 APs alone would take several days, not to mention deployment and configuration. So deployment is very difficult. Additionally, there could be issues with configuration among different users and policies, making FAT-APs very troublesome in large network setups. They are more suited for small networks. In large-scale networking, we mainly use the method of thin APs plus AC, which allows for precision deployment, mass deployment, and implementation of value-added services like billing. So how do we implement this? Mainly through CAPWAP technology. How did the CAPWAP protocol come about? As we mentioned before, there are many proprietary protocols in the wireless network field, with each manufacturer having different technologies. This raises a problem. Devices need to negotiate with APs. Laptops, smartphones all need to negotiate with APs. If one AP is from Huawei and another AP is from Cisco, how will the wireless standards on the phone be implemented? It's not feasible, so the CAPWAP protocol was introduced. We need a mechanism to standardize the various manufacturers' standards. This is the foundation of the CAPWAP protocol. How exactly does the CAPWAP protocol work? How is the CAPWAP protocol implemented? Let's look at its origins. Initially, each major manufacturer had their own technologies like Cisco, Aruba, Siemens, Panasonic. At the time of CAPWAP's inception, it mainly referenced 4 different protocols. First, there was Cisco's LWAPP protocol, which had a very complete message structure and control information, etc. But it lacked a data encryption mechanism. And Cisco's wireless was acquired, not developed in-house. Second was Aruba, also a well-known WLAN company in the industry. Their data encryption technology was quite advanced. We could refer to Aruba's technology to implement its security mechanisms. Siemens and Panasonic mainly served as supplements, for instance QoS, or the connection status of terminals, etc. These aspects could be added as supplements. These are the 4 major manufacturers, 4 different protocols. The CAPWAP working group drew on the strengths of each manufacturer and integrated them into the CAPWAP protocol. Thus, the CAPWAP protocol was formed. We used the general framework of Cisco's LWAPP, Aruba's data encryption mechanism and bridging technology, and Siemens and Panasonic's centralized architecture. This is the CAPWAP protocol, formed by the protocols of these 3 manufacturers. The main purpose of the CAPWAP protocol is to manage APs. Service configurations are done through the CAPWAP tunnel, which can transmit data supervision or issue configurations to APs. This is the specific function of the CAPWAP tunnel. The CAPWAP tunnel is mainly divided into 2 subtunnels. The first is to maintain the state between AP and AC. This includes monitoring AP status, which is part of the management work. Additionally, terminals can also convert data through the CAPWAP tunnel. There are 2 types of messages in the CAPWAP tunnel. One is called control messages, The other is called data messages. Control messages are used to manage APS. Data messages are used to forward users' service data. It uses UDP port numbers. For control messages, it uses 5246. For data messages, it uses 5247. In terms of encryption, most control messages are encrypted, so control messages are more important. Most data messages are in plain text. Another point, the format of control messages and data messages. Control messages contain a control header and message elements. Data messages contain an Ethernet packet. Second, we have encrypted it. If you see DTLS, it means that it has been encrypted. Without DTLS, there is no such mechanism. DTLS provides protection for our messages. So how does CAPWAP connect with AC? What stages must be passed before AC allows AP to come online? Let's look at the overview steps. The first step is DHCP. Initially, AP does not have an IP address. Without an IP address, it cannot interact with AC. So the first step is for AP to obtain an IP address. The second step, AP now has an IP address. Essentially, it has its own ID card to then go and find another AC. AP goes to find AC. Where? That's the discovery stage. Discovering AC. There are various scenarios, but generally, the scenario is AP broadcasts a message to find out where you are. If AC receives it, it responds to AP. The third step is the DTLS connection, which is optional. DTLS, as we mentioned earlier, encrypts the data. This depends on whether you have encryption needs. If needed, you can enable this feature, but by default, it is not enabled. You can skip directly. If you skip DTLS, you move to the join stage. Now that the AP has an IP address and knows the IP address of the AC, the AP will apply to join the AC. To join the AC, not just any request can be accepted by the AC. It checks whether the AP is legitimate. There are authentication mechanisms with several different authentication methods. By default, it uses MAC address authentication. You must manually add the MAC address to the AC to allow the AP to come online. This is the join phase. Once the AC approves the AP's join request, the AP first compares the image data phase. It checks if its own software version matches the software version of the AC. If the AP and AC's software versions match, it skips ahead. If not, the AP sends a request asking the AC to send the version information to the AP. The AP then updates its version and restarts. It skips the image data phase. After skipping the image data phase, it moves to the configuration status phase. This phase just checks whether both parties' configuration files match. But the AC does not send any configurations. The AC simply informs the AP whether they match or not. At this point, the AP records the result. Next is the data check. Nothing needs to be done in the data check stage, just confirm if there are any error messages, and then it's done. Next is the keep alive message, which is about establishing the data tunnel. Actually, the establishment of these two tunnels is not sequential. You can consider them as two independent entities. One is maintained with keep alive, the other with echo request and response. Pay special attention here, for instance. If I ask you what tunnel keep alive maintains, you should at least know it's the data tunnel, not the control tunnel. So, the data and messages used in these two tunnels should be clear to everyone. The run phase is now complete. The tunnel establishment is done. After establishing the data and control tunnels, it's time to move into the configuration update phase. This configuration update request, as we mentioned earlier, records the inconsistent conclusions. The two configurations are different. Here, the AC sends the configuration to the AP, and the AP can update its configuration. This is the overall process of establishing the Keep Alive tunnel. That was the overview. Now let's look in detail at each stage specifically. The first is the AP obtaining an IP address. There are two main methods for an AP to obtain an IP address. The first is static configuration. This involves logging into the AP to manually set a static IP address. This method is somewhat similar to the configuration of a FAT AP. It's quite cumbersome. Therefore, it's not commonly used in medium to large networks. However, some small scenarios might still use static configuration. The second method is through DHCP, setting up a DHCP address pool. The AC will automatically request an IP address from the DHCP server. You can configure the DHCP server on the AC, or it can be set up on the switch. As long as it can distribute IP addresses, it will work. This is how an AP obtains an IP address. Now let's discuss the specific interaction process. We'll break it down into 4 steps. The first step is the AP sends a broadcast message. Once the server receives it, it will reply with a DHCP offer. This is an important point to note. If there are multiple DHCP servers, the AP might receive several DHCP offers. And the DHCP offers do not contain detailed data, just an IP address indicating availability. Then, the AP must reply with a request, which is also broadcast. This broadcast informs all DHCP servers in the broadcast domain which IP address it has chosen. Once the DHCP server receives this, it replies with a DHCP ACK, now with more detailed information. This includes the IP address, lease term, gateway information, DNS, and other information all sent to the AP. Then, the AP truly obtains the IP address. This is the first step. This is not only for APs, but it works the same for others too. It's just more typical for APS. Once the AP has an IP address, it needs to communicate with the AC. So, how does it communicate? Firstly, the AC communicates with the AP through a CAPW AP tunnel. So, the AP needs to establish a CAPW AP tunnel. The first step is to discover the AC. A discovery request. This is a layer 2 broadcast message. I want to discover which AC. I want to find out which AC to connect to. That's the one I'm looking for. If the AC receives the request, it will respond with a message, which is a unicast message. If there are multiple ACs, the AP will choose the one with higher priority or the one with lower load to establish a connection. This is the discovery phase, where the AP establishes a connection with the AC. Why are there multiple? Because there might be scenarios with N+1 redundancy across multiple ACs. This is how the AP discovers the AC. But what if it's a layer 3 network? Then, the AP sends a discovery request from a 10 network endpoint, and the AC is on a 172 network endpoint. Then, the discovery message is useless, because they are not in the same broadcast domain. So, directly in the DHCP phase, the IP address is notified. During the DHCP ACK confirmation, an option can be configured on the DHCP, called option 43, which directly informs the AP of the AC's IP address. That is to say, in other words, when the AP obtains an IP address, it also obtains the IP address of the AC. If there is no option 43, option 15 can also be used. Option 15 works through DNS servers, using domain name resolution to obtain the IP address of the AC. It's generally not used. Option 43 is usually used because by this point, through the DHCP ACK message, the AP is already informed of the address. So this request is a unicast message. I know you are on the 172 network, so directly to the 172 network. Just send the message to this IP address. Unicast to the AC to confirm again, that's it. This is how the AP discovers the difference in Layer 2 and Layer 3 networks of the AC. Let's look further. AP dynamically discovers AC here. It mentioned option 43. ACK includes the specific option 43. Broadcast discovery methods are only suitable for between AC and AP. For Layer 2, capable network scenarios. This is the interaction between AP and AC. After the discovery phase, there is an optional DTLS phase. Whether to undergo the DTLS phase depends on the CAPW AP tunnel and whether encrypted transmission is needed. This is determined by UDP messages. If needed, the message will include a DTLS header and a footer, adding 2 segments in the data. This is the DTLS phase. Join phase. First, the AP sends a join request to join the AC. The AC then responds whether it allows the AP to join. Let's take a closer look at the AP's access process. There's a lot to see here. First, it's determined if the AP's MAC address is on a blacklist. If it's blacklisted, it suggests the AP might be unauthorized and definitely won't be allowed online. If it's not on the blacklist, then it moves on to determining the AP's authentication method. There are 3 different authentication methods for the AP. The first is no authentication, the second is MAC address authentication, and the third is serial number SN authentication. No authentication means direct online access. MAC address is the default authentication method. Then we need to check whether you have manually added the AP's MAC address. If not, then check if this AP is added to the whitelist. If it's not on there either, then the AP can only be placed on the unauthenticated list. It must wait for confirmation. SN authentication works the same, just using different authentication parameters, which are the serial numbers. This is a straightforward process. Just be aware that with MAC address authentication, we need to manually confirm or manually add it. Once confirmed, the AP can go online immediately. This is the AP access process. After the AP access process, we enter the image data phase. Because in the join phase, the AC's join response includes the user-configured upgrade version number. Therefore, here, based on the negotiated parameters, determine whether it's the latest version. If it's not the latest version, then start the software upgrade. The AP sends a request to the AC to download the latest version. Then, the AP begins the software update, followed by a reboot. After rebooting, it repeats the AC discovery, establishes the CAPWAP tunnel, and the join process. This is the image data phase. If the versions are consistent, it directly skips the image data phase. After completing the image data phase, it enters the configuration status phase. Here, the AP sends messages containing the AC name, video information, etc., to the AC. After the AC receives the message, it begins to transition to the next state and sends a response message. It's important to note about the response message that no configurations are sent here. Sending configurations occurs after the run state and are uniformly distributed. Then, the AC transitions to the data check phase. Data check actually doesn't do much other than check for any error codes. If there aren't any, it continues on to the run phase. In the run phase, the data and control tunnels are properly established. When the AP sends a keep alive and the AC receives the keep alive, after responding to the keep alive, the AP enters the normal state. It begins to work normally. Another example is an echo request. The response is the same. The AP sends an echo request. The AC responds with an echo response message to the AP. The AP starts the tunnel timeout timer. After receiving the echo response message, it resets the timer, checking the tunnel timeout. The AP is now online normally. Usually, data packets are sent every 25 seconds, and the private network time is 6 times, which equals 150 seconds. You can imagine, when you unplug the AP's power, it takes 150 seconds for the AC to detect the AP is offline. The data link detection time is quite long. Once you get the AP back online, it won't be immediately online. It also takes some time. If you implement a dual machine hot standby, the waiting time will be correspondingly reduced. This is the process of establishing the CAPWAP tunnel. Following that comes the configuration deployment phase. Here, the AC updates the configuration for the AP. Then, the AC sends an update request to the AP. Upon receiving it, the AP updates and responds with a response message. After this stage, the AP can start to emit signals, allowing wireless terminals to connect to the wireless network. This completes the process of establishing the CAPWAP tunnel. This part explained the process of establishing the CAPWAP tunnel. Now, a new question arises. Now that the AP is broadcasting signals, how does the AP broadcast these signals? And how do the terminals see the AP's SSID? And how can the terminals access the wireless network? These topics will be discussed in our next segment. Thank you, everyone. See you in the next class.